And here we are at negating quantified expressions. We will often want to consider the negation of the quantified expressions. For instance, consider the negation of the statement, every student in your class has taken a course in calculus. This statement is a universal quantification, namely, for all x is a set of p at x, where p at x is the statement x has taken a course in calculus, and the domain consists of the students in your class. The negation of this statement is, it is not the case that every student in your class has taken a course in calculus. This is equivalent to, there is a student in your class who has not taken a course in calculus. And this is simply the existential codification of the negation of the original proposition function. So this next example illustrates the following logical equivalence. For not for all x is a set of p at x if and only if there exists an x such that not p at x. To show that these statements are logically equivalent no matter what the proposition function p at x is and what the domain is, the first note that not for all x is a set of p at x is true if and only if for all x such that p at x is false. Next, note that for all x such that p at x is false if and only if there's an element x in the domain for which p at x is false. This holds if and only if there is an element x in the domain which is not p at x is true. Let's move on to this next example. This example illustrates the equivalence. There's not exist x there's not exist in x in a set of q at x if and only if for all x such that not q at x. To show that there's not exist x in a set of q at x and for all x such that not q at x are logically equivalent no matter what q at x is and what the domain is. The first note that this statement is true if and only if there exists and q at x is false. This is true if and only if no x exists in the domain for which q is true. Next, note that no x exists in the domain for which q at x is true if and only if q at x is false for every x in the domain. Finally, note that q at x is false for every x in the domain if and only if not q at x is true for all x in the domain, which hold if and only if for all x such that not q at x is true. Putting these steps together, we see that there's no exist x in a set of q at x is true if and only if for all x such that not q at x is true. We conclude that there's no exist x in a set of q at x and for all x such that not q at x are logically equivalent. To wrap up this 1.4.9, this section dives into how to negate the statements involving quantifiers like for all and there exists. Remember, these quantifiers are used to make statements about a set of elements. Translating from English into logical expression. Translating sentences in English into logical expression is crucial task in mathematics, logic programming, artificial intelligence, software engineering, and many other disciplines. We began to study this topic in section 1.1 where we use propositions to express sentences and logical expressions. In that discussion, we purposely avoided sentences whose translation required predicates in quantifiers. Translating from English to logical expressions become even more complex when quantifiers are needed. Let's say, express the statement, every student in this class has studied calculus using predicates and quantifiers. So these are the extra examples. Solution. First, we write the statement so that we can clearly identify the appropriate quantifiers to use. In doing so, we obtain for every student in this class, that student has studied calculus. Next, we introduce the variable x so that our statements become for every student x in this class. X has studied calculus. Continuing, we introduce C at X, which is the statement X has studied calculus. Consequently, in the domain for X consists for the students in the class. We can translate our statement as for all X in the domain C at X. However, there are other correct approaches in different domain of this course, and that other predicates can be used. This approach we select depends on the subsequent reasoning we want to carry out. For example, we may be interested in a wider group of people than only those in the class. If we change the domain to consist of all people, we will need to express our statement as for every person X. If person X is a student in this class, then X studies calculus. If S at X represents the statement the person in this class, we will see that our statement we express as for all X at S at X implies C at X. Finally, we are interested in the background of people in subject besides calculus. We may prefer to use two variable quantifiers, Q at X and Y, for the statement student X has studied subject Y. Then we should replace C at X by Q at X slash calculus. In both approaches to obtain for all X in a set Q at X calculus, or for all X such that S at X implies Q at X calculus. In the example 23, we displayed different approaches for expressing the same statement using the predicates and quantifiers. However, we should always adopt the simplest approach that is adequate for the use in subsequent reasoning. So to wrap up the 1.4.10 section, this section is likely focuses on to how to translate everyday English statement into formal logic expressions using predicates and quantifiers. Predicates are statements about variables, and quantifiers specify on how many variables satisfies the predicate. For instance, you might learn how to translate all students like pizza into a logical expression with variables and quantifiers. And we're almost done. We're at 1.4.11, using quantifiers and system specification. In section 1.2, we use proposition to represent system specification. However, many system specification involve predicates and quantifications. This is illustrated in example 25. Use predicates and quantifiers to express the system specification. Every mail message larger than 1 megabyte will be compressed, and if a user is active, at least one network link will be available. So as you can see on the extra example, let S at M and Y be a mail message. M is larger than Y megabytes, where the variable X has a domain of all messages and the variable Y is the positive real number, and let C at M denote mail message M will be compressed. Then the specification every mail larger than 1 megabyte will be compressed. Can be represented also as for all A at M and a set of S at M1 implies C at M. Let A at U represent user U is active, where the variable u has a domain of all user. Let S at n and x denote network link n is in a statement x, where n has a domain of all network links and x has a domain of all possible states for a network link. Then specification: if a user is active, at least one network will be available, can be represented by for all u in a set A at u implies there exists in u in a set of A at u implies there exists n such that S and n is available. To wrap up this subchapter, using quantifiers and system specification, this system might explore how quantifiers are used to precisely define the requirements and behavior of the system. In software development, system specification outline what the system should do. Quantifiers can help express this requirement clearly. As you can see in the example, it's more about the specification and the requirements on how to execute precisely and make it a logical to illustrate it logically. Examples from Lewis Carroll. Lewis Carroll, the author of Alice in the Wonderland, is also the author of several works on symbolic logic. His book contains many examples of reasoning using quantifiers. As you can see on example 27, 28, 26, and 27, the first two are called premises and the third is called conclusion. The entire set is called an argument. The first statement: all lions are fierce. Next, some lions do not drink coffee. Some fierce creatures do not drink coffee. In section 1.6, we will discuss the issue of determining whether the conclusion is a valid consequence of the premises. In this example, it is let P at x and Q at x and R at x be the statement x is a lion, x is fierce, and x drinks coffee, respectively, assuming that the domain consists of all creatures. Express the statement in the argument using quantifiers P at x, Q at x, and R at x. These are the solution on the statement above. We can express the statement as for all x in a set P at x implies Q at x. On the second note, there exists an x in a set P at x and not R at x. On the last one, E at x such that Q at x and not R at x. Notice that the second statement cannot be written as for all x P at x implies not R at x. The reason is that P at x implies not R at x is true whenever x is not a lion, so that there exists an x in a set P at x implies not R at x is true as long as there is at least one creature that is not a lion, even if every lion drinks coffee. Similarly, the third statement cannot be written as there exists in a set Q at x implies not R at x. So, to wrap up this point 12 examples from Lewis Carroll, this section is likely presents example of logic puzzles or paradoxes from the writings of Lewis Carroll, a famous author who also explored logic in mathematics. This example might be used to illustrate the concepts of predicate and quantifiers in a fun way. And we are at our last juncture. The logic programming, an important type of programming language, is designed to reason using the rules of predicate logic. Prolog, from programming logic, developed in the 1970s by computer scientists working in the area of AI, or artificial intelligence. As an example of such a language, prolog programs include a set of declaration consisting of two types of statement, which are prolog facts and prolog rules. Prolog facts define predicates by specifying the elements that satisfy these predicates. Prolog rules use to define the new predicates using those already defined by prolog facts. As you can see on the example 28, it says that consider a prolog program giving a fact telling it the instructor for each class and which student classes are enrolled. The program uses these facts to answer queries concerning the professors who teach particular students. Such a program could use a predicate instructor PC and enrolled CS to represent that Professor P is the instructor of course C and that student S is enrolled in the course C respectively. For example, the prolog fact in such a program might include this: Instructor Chan in the Math 273, Instructor Patel in the EE222, and so on and so forth. Lowercase letters have been used for entire entries because prolog considers names beginning with an uppercase letter to be a variable. A new predicate teachers PS representing the professor P teaches the student S can be defined using the prolog. Teaches PS, instructor PC, enrolled CS, which means that teacher PS is true if there exists in class C, such that Professor P in the instructor class of C and student S is enrolled in class C. This prolog answers queries using the fact and rules it is given. For example, using the facts and rules listed in the query. Enrolled Kevin Math 273. It produces the response yes. Why? It's because Kevin is enrolled on that certain course. Because the fact that enrolled Kevin Math 273 was provided an input, the query responses that who are the people that are enrolled on this course, it would respond Kevin and Kiko. Because makita naman diri sa ang enrolled sa Math 273 kay C, Math, and Kiko. That is why the response will be those names. To produce this response, prolog determines all the possible values of x for which enrolled x, Math 273, has been included as a prolog fact. Similarly, to find all the professors who are instructor in classes being taken by Joanna, we use the query teaches x Joanna. This query returns Patel and Grossman. Nga naman yung query nga puput up inani Patel Grossman. It is because Professor Joanna has a student enrolled named Patel and Grossman. Ano siya? Interrupt up all on this point 13 logic programming. This section introduces a programming paradigm called logic programming. Logic programming statements are used to represent knowledge and solve problems. Quantifiers can be used within these logic programs. That is all. Thank you.